Welcome back. We'll continue with our topic uniform continuity. The last video we have learned about uniform continuity and the difference between uniform continuity and continuity. So it will be a good exercise for us to see that a uniformly continuous function is continuous, but a continuous function may not be uniformly continuous. We already have an example how to verify that some functions are not uniformly continuous. We have a definition of uniform continuity and we know how to verify uniform continuity. But if some function is not uniformly continuous, how to verify? Basically, it's a negation of the definition. The definition says that given epsilon greater than 0, there exists delta for which something should work. Negation should be for some fixed epsilon, no delta should work. That means there should be at least one epsilon for which no delta should work. Let us apply it to the function f of x equal to x square on R. Fix epsilon equals 2 and let delta strictly greater than 0 be arbitrary. If we choose a natural number n naught such that 1 over n naught is less than delta, then we denote that n naught to be y, say nx is n naught plus 1 over n naught. It's easy to see that x minus y is 1 over n naught, which is less than delta, but f of x minus f of y, simple calculation tell us that it is strictly greater than 2. That means it is strictly greater than epsilon. Hence, this function is not uniformly continuous on R. Now I can take various simple examples like f of x equal to x cubed, or say f of x equal to some other polynomial, f of x equal to e to the power x, and so on. One question we might face that how to fix this epsilon or what we should take epsilon to be. This comes with experience and practice. So given a function, we try to verify the definition. That means for some fixed epsilon, try to see that f of x minus f of y less than epsilon. For x minus y less than delta. And the proof will recognize if there is any problem, and depending on that, we can verify for what value of epsilon we can work on to show that some function is not uniformly continuous. Let us move on to some category of functions which are always uniformly continuous. Definition: a function f from a to r is called ellipsis function if there exists a constant L strictly greater than 0 such that mod of f of x minus f of y is less than equal to L into mod of x minus y for all x. Such a function is called ellipsis or ellipsis continuous function. It is easy to see that ellipsis continuous functions are uniformly continuous, because whenever mod of x minus y is less than delta, this quantity on the left hand side is less than L into delta. So if we take epsilon equal to L into delta, or on the other hand, delta equal to epsilon over L, show mod of f of x minus f of y is less than epsilon whenever mod of x minus y is less than delta. So given epsilon greater than 0, we can choose delta to be epsilon over L and we are done. The function f of x equal to x square is ellipsis on any bounded interval a comma b, and hence this function is uniformly continuous. Because we know that ellipsis functions are uniformly continuous. To check ellipsis continuity, f of x minus f of y turns out to be mod of x plus mod of y into x minus y. X and y belonging to a closed interval a comma b can be bounded by 2 into maximum of mod of a comma mod of b. Taking this to be L, we have f of x minus f of y is less than or equal to L into mod of x minus y. We can also verify that f of x equal to x square is not ellipsis on R. So we can start with that. Let it possible f is ellipsis on R, then there will be a constant L greater than 0 such that f of x y modulus of that is less than or equal to L into mod of x minus y. Now we can always find x and y such that mod of x plus y is greater than L, which should contradict the definition. Hence, the function is not ellipsis on R. We also know that this function is not uniformly continuous on R, but the function being not ellipsis does not imply that f is not uniformly continuous. Our point being, ellipsis functions are uniformly continuous, but a uniformly continuous function may not be ellipsis. Here's an example: f of x equal to square root of x. See assignment. Finally, a very important result: connecting continuous and uniformly continuous function. Every continuous function on a closed and bounded interval is uniformly continuous. So given a function on a closed and bounded interval, if we know that the function is continuous, we do not have to verify whether it is uniformly continuous or not. It is guaranteed. So we have learned about uniform continuity of a function, how it differs from continuity, how ellipsis continuous function or ellipsis function is always uniformly continuous. Thank you.